this video, we're going to be looking at the definition of the derivative, and we're going to investigate things like average rate of change and instantaneous rate of change. We'll define what the derivative means, we'll define what it means for a function to be differentiable, and we'll do a bunch of example problems. So, first I want to just define average rate of change, which is hopefully something you've seen, in a previous course. So, we're going to say that the average rate of change of a function f over some closed interval, say a to b, is given by, we're going to define it to be, well, the change in f divided by the change in x, right? So it's going to be f of b minus f of a over b minus a. Okay, this looks like slope, and it is. It's y2 minus y1 over x2 minus x1. Okay, it is the same idea as the slope between 2 points. Okay, now suppose that we've got some kind of function, and it's really not going to be that interesting unless it's curved. Maybe this is my y-axis, and that's my x-axis. And so I've got this graph drawn over the interval, looks like -1 to 5, we'll make it 6. Okay, we can find the average rate of change over the interval -1 to 6. I'm going to actually, do a kind of a more limited scope here. And, because this isn't intersecting at a grid point. So let's say the average rate of change over the interval 1 to 5. Okay, just assuming a scale of 1 in both directions. So if this is the graph of f, the average rate of change of f over the closed interval 1 to 5 is going to be f of 5 minus f of 1 over 5 minus 1. Okay. And that's going to be, well, f of 5 is looking like 4, f of 1 was 1, so 4 minus 1 is 3, over 5 minus 1 is 4. Okay. I do need to point out that this is also, graphically, in terms of looking at this graph, this 3/4 is the slope of the line that connects the points 1 and f of 1 and 5 and f of 5. And we'll call that the secant line. So I'm going to actually draw it in here, and I should have got a better straight edge, but I don't know that I have a better straight edge at my house right now. So we go over here, and we're going to kind of draw in a dotted line in red. Whoops, that's on the little pad. And then we see that that's the slope, right? It rose 3 when it ran 4. Okay, so we call this the secant line. Okay, now if we wanted to find out, what was the slope of the function f right at this point, that's something that we could definitely approximate by, it looks like it's going to be pretty close to the secant line, but it's not exactly it, because you can see it's a little shallower here than the steepness of this line. And so the instantaneous rate of change is going to, in a couple of minutes, be the slope of the tangent line rather than the slope of the secant line. But we don't really know how to find that yet, right? It's like I could try to draw a little line in and extend it and count squares, but that's pretty much our only technique at this point. Okay, now we'll be using kind of the techniques that we've looked at throughout this unit to find a slope of a tangent line, but that'll be in a couple minutes. So I've got another example for you. Okay, and this one is going to be related to a free response question from the AP exam. All right, here's one I just grabbed from 2016. This is not exactly how they asked the question, but this is essentially the question that they asked. They said that water is getting pumped into a tank at a rate of R of T liters per hour, where T is measured in hours. And it's asking, what's the average rate of change of R over the time interval 1 to 3? Okay, well, this is going to be R of 3 minus R of 1 over 3 minus 1. It's really good to write this. I graded a question for Calculus AB this summer that was something similar to this, and you were able to get 1 point for the answer. And, you know, if you got the answer right, it was kind of implied that you did it this way. But if you made an arithmetic error, but you didn't write the general difference quotient, you got no credit. And you could have gotten partial credit by just writing that I'm interested in finding the difference quotient and then plugging in the numbers. So it's going to be a good strategy for us to take. Is to kind of write down the formula that we're going to use, and then we're going to actually apply it. So it'll be 950 minus 1190 divided by 3 minus 1. Okay? And that's actually a safe place for us to stop in this class, because this is a number that is equivalent to the right answer. Okay. Now this is a calculator question, so you would have had a calculator right next to you and you probably would have just felt like doing it anyway. Or maybe you're good at arithmetic and you see you're dividing by 2, and you know there's a good chance you can do that by hand. The thing about this question is that they almost always ask you to indicate units of measure. Okay, and that's something that's going to be really big for us. They say that R of T is measured in liters per hour. Okay, and so to do this kind of like somebody I know, I'm going to put this in brackets. I think that's what scientists do. Or I've seen a scientist do it before, and I definitely hadn't seen it before, so I assumed it was a sciencey thing. This is in liters per hour, and time is measured in hours. Okay. And if we're looking at the rate of change of f of x with respect to x, the units of the rate of change will be the units of f divided by the units of x, or the units of the dependent variable divided by the units of the independent variable. And then I'll try to come in with an interpretation here in a second. So if they say indicate units of measure, you can say liters per hour, or liters divided by hour, divided by hour. You could say, in words, liters per hour per hour. You can say liters per hour squared if you want. And I don't really understand what a square of an hour represents, so I prefer to write it like this. This makes sense to me. Okay, so when I say liters per hour, what I'm really saying is, maybe I'll actually get the value of this. So I don't want to do anything. Okay, so it's negative 240 divided by 2, and that's negative 120. And what you're going to find that this means is that over the course of the time interval 1 to 3, the rate at which water was getting pumped in was decreasing 120 liters per hour each hour, right? Because over the course of 2 hours, the rate decreased from 1190 liters per hour to 950 liters per hour, which was a decrease in 240 liters per hour over the course of that 2-hour time interval. And that's the average rate of change. All right, next I'm going to say, what if I'm interested in the instantaneous rate of change? Okay, we're interested in instantaneous rate of changes all the time. You know, the policeman, when he's sitting there in Lakeway, is interested in your instantaneous rate of change of position with respect to time, right? He's checking to see if you're speeding. He's speed, which is going to be an instantaneous rate of change of your position. Okay. How do we find that in just an instant, as opposed to, you know, saying, oh, well, you went 1 mile in less than 1 minute, meaning you had to have been averaging over 60 miles an hour, which is far too fast for Lohmann's crossing or whatever. You know, they're not going to do that, right? They're going to use a radar gun or something. It's somehow measuring your instantaneous rate of change. So kind of the thing that I like to start with is a function that we're all really familiar with. Draw you a good picture of it, and that's y equals x squared. Okay, I'm mainly only interested in it over here. So 1, 3, 5. Okay. So this is the graph of it, and maybe I can even, I don't know if I'm going to run off the page, but or off the screen, but yeah, it looks like I did, but that's fine. I'm not going to shift it. Now, I don't know if this is going to work because this is a new document camera to me. So what I'm going to do is I'm going to say, you know, what if I'm interested in, I don't know, say the slope of this curve at the point where x equals 1, right? I know it's, if I was to draw in a tangent line, it would have positive slope, okay? But, you know, kind of what trajectory is this curve taking? That's another question that's equivalent. And so what we could do is notice that if we zoom in really close on any particular piece of this curve, and so I'm going to actually do that. We'll see how close this thing can zoom. Not that far. Oh, is it still going? Okay, the old document cameras really were better about this. They could really zoom in close. But if you look, you can see that it looks kind of closer to a straight line. Right? And if you continued to look, it would look more linear the closer you looked. So now you're probably going to have to listen to me clicking this machine while I zoom back out. But that's going to be the idea, is we're going to look at the slopes from a closer and closer perspective. Okay? So a pretty decent approximator for the slope of the tangent line here would be, I don't know, maybe the slope of the secant line between these 2 points. It looks like it's pretty close to parallel. Okay. So, you know, you're thinking about this. And this is usually the type of thing I would be drawing on a whiteboard or a chalkboard and erasing, and it's just not going to work in this situation. But you see that, you know, it's a decent but not perfect, right? And that was not the best dotted line ever. And I'm going for this thing that I'm going to draw in blue, which is going to be the tangent line, which you see it's not quite the same. I didn't quite draw that right. I can tell because I know what the slope of the tangent line is there. Okay, so what we need to do is we're going to need to consider the limit of the slope of the secant line as these points get closer and closer to the point of tangency, the point that we're interested in. So what I'm going to do is I'm going to say, I'm just going to define the instantaneous rate of change to be the limit as B and A go towards each other. Now this is very non-mathematical, right? But this is kind of what the intuition that I want you to So as we're getting these 2 points closer and closer together, what's the limit of this slope, right? Does this limit even exist? Okay, the limit of rise over run is going to be our slope at a point, or our instantaneous rate of change, or our definition of a derivative. Okay, but this doesn't really make a whole lot of sense. And is we're going to say, we're just going to say, as x approaches a, of f of x minus f of a, over x minus a, where, you know, a is our point that we're interested in. Say this is a. Okay. So that will be our definition of the instantaneous rate of change of f at a point a. whoops, I've run out of space. Instantaneous rate of change of f at x equals a, and I'm going to just have to squeeze that in. Is given by this limit. And we're going to denote it with f prime of a. Okay, and this means generally the slope of f at a. Okay. Now, if f is a linear function, we have the tools to find out what f prime is, right? Past that, we really don't. Okay, we don't really know anything else. Yet, I will give you all the tools to find these slope values, these instantaneous rates of change. Okay. Now, as it goes, it's going to be useful for us to talk about the instantaneous rate of change of a function at more than one x value. Okay? And so we're going to talk about a function that gives the slope of another function at any x value. Okay? And then that will be the derivative function. But before we do that, I am also going to show you another form of this limit that can sometimes be a little easier to work with. And it's equivalent. And remember, this is the limit of rise over run as run is going towards 0, right? We're going to look on a really narrow x interval and try to get the slope of just that line segment. Because we would think that, you know, if I was to pop this out, you see what I'm saying here? If we looked more closely with a magnifying glass, we would see that it looks closer to that. We could take the average rate of change over these 2 points to get a line segment, and then that would be a better representation of the slope at this middle point. Okay, so it's the limit of rise over run as run goes to 0. So I'll say f of a plus h minus f of a divided by h. And these are equivalent, and I'd let you kind of work through the algebra to show how these are actually the same thing. Okay. Anyway, that's you know, another version of that same limit. And this can be easier to work with, especially if you are in the type of calculus class where you need to, you know, show what the derivative of 5x to the third is algebraically by hand. Okay, that's going to be the way that you want to do it, is using that one. But I'll talk to you more about that at a later time. Okay, so the derivative function we're just going to call it f prime of x. And so it gives the slope, or the instantaneous rate of change, and I'm just going to say slope because it's, you know, this class does not rely on rigorous definitions and theorems. It relies mostly on intuition and problem-solving ability. So f prime of x gives the slope of f at, you know, various x values. Okay, there will be times where there isn't really a slope that we can put on a function. Like, if you think at a vertical asymptote, what are we going to do with, like, there's no function to even put a slope on, right? So it wouldn't make sense. F prime of x doesn't always make sense, but any place where it does make sense to have a tangent line or an instantaneous rate of change, then this will be defined. Okay? And I'll show you all the cases where it would be undefined here in a couple minutes. Okay, and okay. F prime of x gives the slope of f at various x values and is given by pardon me, got distracted and kind of lost my place. So we're talking about the derivative function, and the definition of the derivative function is going to be the limit as h approaches 0 of f of x plus h minus f of h divided by h. This limit of rise over run. Okay, and I'm not even going to go into showing you how to, prove that the derivative of x squared is 2x or any of these things using the limit definition. I might do that later on. I'll definitely show you in general using this definition why the power rule, product, quotient, chain rules, all these rules that we're going to have, I have videos of the proof of them using this definition. But you just need to think, it's the limit of rise over run as run goes to 0. Right? What's the effect of, bumping up x by a little bit, in terms of, okay, was it f of a at f of x? Excuse me, I wrote this down wrong. This is minus f of x. It's like, why would I have f of h? Because f of h going to 0, this is going to be f of 0. Okay, that's what I wanted. Okay. What's the effect on f of x by bumping up x by a little bit? That's the rise, divided by the run, which is actually h. All right. Now, we will say that, for each x value that this limit exists, function f is differentiable. So I'm going to write that out real quick. All right, so when we say differentiable, we mean that the derivative exists. Okay, so we say f is differentiable at a point x equals a if f prime of x exists at x equals a. Okay. Basically, that this limit where x equals a, or this limit at x equals a, and I'm realizing I changed that b, but I didn't change that b, so I'm going to do that now. And so if that limit does not exist, if f prime of x does not exist at x equals a, we would say that f is not differentiable. And I'm going to show you ways that that limit could not exist. All right, so there's going to be kind of 3 main ways that a function could be not differentiable. And it's going to be related to that limit not existing. Okay, so the first way is going to be at a sharp turn or sharp corner. Now, I'll talk to you more about this in the class meetings and stuff, but I also graded for a problem where they were asking for a derivative value at a sharp corner, and the answer was that the derivative didn't exist because of the sharp corner, and there were certain, words, and there was some terminology that was okay to use, and there was some that was not okay to use. Okay, sharp corner was definitely okay. Cusp was pretty common as well. Corner seems to really indicate what I'm talking about, where we have a sudden change in direction. Now, sudden change in direction, oddly enough, was not something that got you credit on the AB exam for that particular problem. I believe that was number 2 form E3 or something, something that not even that many kids had. And kind of a function that I'm going to talk about right here is one that we actually already know about, is like an absolute value function. And, just for fun, I'm going to transform this thing a little bit just so that it's kind of also centered in my window. I'm going to call this f of x. All right. Now, we know we could, if we had to, we could write down a formula for f of x. F of x is probably equal to -1 plus the absolute value of x minus 2, but I don't really need to worry about that. I'm going to say that f prime does not exist at x equals 2 because the limit, and let's actually look at this, the limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. Okay, this limit doesn't exist. Okay. I'm just telling you because of the sharp corner. but let's figure out why this limit doesn't exist. Okay, if x is approaching 2 from the positive side, then I've got, like, say, f of 3 minus f of 2 over 3 minus 2. That's the slope between these 2 points. That's 1. Okay. Well, from over here, if I chose, instead of 3, I chose 2.5 or 2.1. Well, I'm still going to get a slope of 1 because the slope on this entire portion of graph is always 1 because it's a line. Okay. Now, from the left, I'm going to see that these limits are coming back negative 1. The limit is coming back negative 1 as x approaches 2 from the negative side, because the slope of this line is negative 1. So the two one-sided limits disagree. And I'm going to be really specific. I'm going to say limit as x approaches 2 from the negative side of f of x minus f of 2 over x minus 2 is equal to negative 1, while the limit as x approaches 2 from the positive side of this difference quotient, whoops, okay, and this is positive 1. Okay, disagreement in the one-sided limits means this limit doesn't exist and the derivative does not exist. Okay, so it's not differentiable at a place where there's a sharp turn because the derivative goes from something suddenly to something else, right? It's not smoothly happening. Okay. A second thing that can happen is a vertical tangent line. And that would be, the derivative is the slope of the tangent line. And if a line is vertical, then it doesn't really have a well-defined slope, something you saw in Algebra 1. So kind of the function that you are familiar with that this happens on is y equals the cubed root of x. So, it goes kind of like this. And, we don't always draw out the best, but it comes up and it's very vertical because cube root is related to the graph to the third, which is very flat at the origin. And I would let you think about that. All right, and it's because this limit doesn't exist due to unbounded behavior. Okay, so I'm going to, again, I'm going to say the limit as, just a second, as x approaches 0 of f of x. Well, f of x is cube root of x. Maybe I'll just write it like that, see if there's anything we can see from that. Cube root of x minus f of x is 0 over x minus 0. Okay, well, what's interesting about that is that this limit doesn't exist because if we go in and we simplify, this is cube root over, this is x to the 1/3 divided by x to the 1, which gives you x to the 2/3 in the denominator, and as x goes to 0, that fraction goes to infinity. So you can see that this limit does not exist due to it going to infinity. Okay. That's another reason that a function could be not differentiable. All right, and now the third reason I'm going to tell you about, but I need to tell you about something else first. I need to tell you that if a function is differentiable at a point, then it is guaranteed to be continuous at that point. It's an if-then statement. If differentiable, then continuous. Differentiable implies continuous. Now, no opposite relationship does not hold. We just saw two cases, right, where we saw two functions that were continuous, right, because there was no jump or hole in the graph or anything, but they were not differentiable. Okay, so continuous does not mean differentiable, but differentiable necessarily implies continuous. And these functions are differentiable at, really, this one is differentiable everywhere except for x equals 2, and this one's differentiable everywhere except for x equals 0. Because there's a nice slope here. It's looking pretty shallow, and it's positive. Okay, so I go back over here, and I say that, important note, the converse does not hold. Okay, continuous does not imply differentiable. And, okay, I've just barely gone off the edge. Okay. So I've just been very clear. If differentiable implies continuous, but continuous need not necessarily imply differentiable. Okay. Now, there is kind of another, I'm not sure if I would even really consider this a corollary because it's just the contrapositive. But if f of x is discontinuous, if it's not continuous, then it doesn't have a chance to be differentiable. Okay, and that's the contrapositive. And I'll tell you more about that in a second. If f of x is not continuous, I should have said at x equals a because we mostly just defined continuity at a point. At x equals a, then f is not differentiable at x equals a either. Wait, yeah. Okay, so that means that the derivative cannot exist at a place where the function is discontinuous. And what I typically say is, and now this was not true when I played football, but I'm pretty sure that this year at our school, if you are on the football team, then it necessarily implies that you are a male student. But as we know in any of our classes, you look around, and it's not going to be the case that every male student is going to be a football player, right? Okay, but if you have a student that is not a male, they are not going to be on the football team, right? If all of the students that are on the football team are male. If football, then male. If not male, then not football. But you can't say anything about if not football. There's all sorts of people that don't play football. Okay? And that was just for this particular example. And that's why, if the function is not continuous at a point, it doesn't have a chance to be differentiable. Now, you might be saying, I don't believe you. I don't believe you that differentiable implies continuous. And if that's you, then I would kind of direct you down to the description of this video, because there should be linked to it a video of the proof of this theorem. Okay? It's very at y'all's level and easy to understand. Okay. So I think I am ready to just write out a bunch of example problems for the rest of the time. And this is already a pretty long video, so I'm going to try to go pretty quick through the examples, but I'm going to give you a variety of problems that this could relate to. All right, first we have a pretty direct one. Here is the graph of a function f of x. And f's graph, oh, I realize that's a little confusing. This is f's graph, not f prime's graph. F's graph consists of two semicircles and two line segments. Where is f not differentiable? Okay, well, we know that a function is not differentiable anytime where there's a sharp corner. Okay, so x equals 3, sharp corner. Okay, at x equals 4, there's a jump discontinuity. There's nowhere to even put a tangent line if you wanted to, right, that fits in with the overall behavior of the function before and after. Right, thinking about the limit from both sides. And you can say discontinuous. Okay, and at x equals 6, we've got a vertical tangent, right? Because it's two semicircles. I know that kind of at the edge of a circle, it's pretty vertical, and at the beginning, it's a horrible drawing, but the tangent would be vertical here because of the fact that they're semicircles. Okay, so that's a pretty direct question about differentiability. But there's another way I could ask you. All right, so this is a situation that I have seen on multiple choice questions before. Here's a picture of the graph of the derivative. Is the function f differentiable at x equals 3? Okay, now I asked, where is f actually not differentiable? Because I'm telling you that f is differentiable at x equals 3. F prime is clearly not differentiable at x equals 3 because of a sharp turn. But I'm telling you that f is differentiable at x equals 3 because f prime of 3 is equal to 2. Okay, now we haven't talked about the second order derivative, and that'll be something we talk about at length in this course, but I'm just saying that the slope of f is well defined because f prime of 3 exists here. Okay, what this means in terms of the behavior of f, we're not really ready for that yet. We're just going to have to think about this situation more. But I'm telling you, the slope of the tangent of the line tangent to the graph of f at the place where x equals 3 will be 2. Okay, so there will be a tangent line, it will be differentiable, and the tangent line will have slope 2. Okay. F is not differentiable at x equals 1 because the derivative doesn't exist. And you'll have to pardon me, it's kind of overcast outside and the clouds are shifting and I'm sitting right by a window and so the lighting is kind of shifting. And I can tell that that's kind of causing issues with the video, but I'm trying to minimize it by closing the blinds as much as possible. Let's see. Be darker for now, but maybe if I turn on, yeah, it's adjusting. It seems to help. Throw on the lamp. Maybe the lamp isn't a good idea. All right, so x equals 3 because f prime of 3 is 2. Okay, f is not differentiable at x equals 1. Because f prime of 1 doesn't exist. What this most likely looks like on the graph of f is actually just a hole in the graph of f, where there's a well-defined limit. A place where there's a vertical tangent, you would actually see a vertical asymptote in the graph of the derivative, probably. And that's, it would probably be for the cube root one, you would see a vertical asymptote where both went towards positive infinity because that's kind of the direction that the slope is going. It's going from positive to positive and huge to positive and less huge. So it's going to infinity and then back down, but still positive. Okay, so this is differentiability by looking at the derivative. I've got a bunch more. And something I realized that might have been good for me to add into this example would have been a jump discontinuity in the graph of the derivative. So that's actually what I'm going to do. I'm going to change this to maybe be like that, this derivative. Just when I was looking at this, getting the next problem ready. And to talk about at x equals -1, this is the evidence in the derivative of a sharp turn in the graph, right? It went from having slope +1 to having slope -2 immediately, okay? And that's going to be a sharp corner on the graph of f. All right, another quick one I've got is if g of x is equal to 1 minus the absolute value of x plus 2, find the value of g prime of -5, g prime of -2, and g prime of 0. Okay, so at this point, all we really have as an option to us is to draw a picture of the graph. And so I am assuming that you're able to draw a picture of the graph of 1 minus the absolute value of x plus 2, or at least know kind of what it looks like. It's going to be like an upside down absolute value thing that's shifted left by 2 and shifted up by 1. So it's probably going to look like that. And since it's regular absolute value, it's not drawn to scale, 2, yeah, actually, it's pretty decent. Is going to be, okay, we know what the slopes of these things are. It's +1 and -1. So g prime of -5 is the slope here on this section, probably all the way down here, right? If that's -2, then -5 is going to be way down here. But the slope will still be +1. Okay, g prime of -2 is the slope here at the corner point, which does not exist. Okay, and then g prime of 0 is going to be, okay, the slope over here when I actually do intersect the y-axis, and that's going to be -1 because of the nature of this absolute value function. Okay, so the line tangent to h of x at x equals 1 is given by y equals 2x plus 3. Find h of 1 and h prime of 1. Okay, well, I'm going to start with the easy part. Okay, the easy part is going to be h prime of 1, because remember, h prime is the slope of the tangent line to h at the point where x equals 1. But I know the slope of the line tangent to h at the point where x equals 1. Right? It's 2. Okay, I've got the equation, and the slope is 2. So I'm going to say h prime of 1 is equal to 2. Okay. Now, h of 1 is going to be like, well, okay. Suppose we've got, and maybe I could even, I'm going to draw probably more than we need. 2x plus 3, though. Right? And I don't know, I don't really have enough information to say, this is the tangent line. I don't know if h is curving, you know, kind of like that, or like that. Okay? Or if it's just that straight line, I don't know, who knows. But the line tangent does have slope 2. So if h was curved like this, that would work. Or if it was curved like that. But either way, h of 1 is certainly 1, 2, 3, 4, 5. And how we would find that is just by plugging in 1 to the tangent line, because the point of tangency is shared by both the curve and the tangent line. Okay, so it's 2 times 1 plus 3, which is equal to 5. Okay, so that's kind of an introductory level tangent line question. All right, the last two examples I've got are going to be curve sketching. And this is going to be a skill that we're going to work on throughout the course. So if you are, this is the type of thing where if you have trouble with it the first time, you're going to get so many opportunities to continue to look at the graph of a function and sketch the graph of its derivative that it's really not a big deal. And today we're really just starting out with this. And we only know a little bit about the meaning of the derivative, and we're going to learn so much more about it that it'll make this much easier. But we're just going to start off with a function, and I'm going to make sure to just give it some, you know, I'm only going to graph it in the first quadrant on 1 to 5, and I'm going to make it have some pretty clear characteristics. Okay, I'm going to make it start off here at 1. And then it's going to come up here, and then maybe it'll kind of bottom out and then go over there. Okay, so I'm going to make it pretty smooth. I want it to be differentiable everywhere. Okay, and that'll be good for me. Okay, so this is the graph of f. Okay, now if I want to draw the graph of f prime, remember that f prime is the function, it's the derivative function that gives me the slope of f at a given x value. Okay? And I'm not going to be able to go in here and find out what of, you know, f at any of these points. I'm only going to be able to say whether it's positive, negative, or possibly 0. Okay? So I'm going to start with, we see that the behavior of the function is really like 3 different pieces, right? It goes up, and then it comes back down, and then it goes back up. And that is actually going to be enough for us to give a pretty decent sketch of the derivative. Now, a little bit of advice, sketching the graph of the derivative, you kind of want positive and negative territory, because we see that at some places the slope of the tangent line is going to be negative, right? Okay, so at first, the slope at the beginning, right, I'm going to draw the slope of the tangent in blue for the first segment, is positive, right? It looks like it might be like about +2 or something. I'm not even going to worry about that. I know it's positive, but it's kind of getting shallower as I'm approaching. And at the top, the tangent line would be horizontal. Okay, and a horizontal line has no rise for a given run, meaning it has slope 0. So this is going to be a place where we have a 0 slope. So at x equals 2, the value of the derivative is 0. Before, it's positive, but it's kind of getting flatter, so it's decreasing towards that. Okay, so maybe something like, I don't know, that. It does not have to be a good sketch. Then, after it, I'll switch over to red, and I'll see that the slopes are, all of a sudden, they're getting negative, and they're getting pretty steep. So they're pretty negative. But then, you know, if this is actually the minimum value, I didn't draw that very well. Let me see if I can resketch. Make it so that it really is, without looping back on itself. Alright, like that. That's the best I can do. But we see that the slope of the tangent line is very negative going for a while. So, but then, by the time we come back around here, you know, it's getting shallower, and at the minimum, it is another 0 slope. Okay, I'm going to do another one of these where it doesn't go as suddenly, and we can see this a little more clearly. Okay, so it goes negative for a while, but then by the time I go to x equals 3, it's back to 0 again. So maybe it's like, you know, really down there for a while. But then it comes back. And then, okay, over here in this last part, which I will label in green, it's positive but pretty shallow, but eventually getting steeper. Okay, so get positive and increasing. Okay, so I'll say it goes positive, but it's kind of increasing. Is pretty much what I'm seeing. This is, of course, as best I can do. I don't know if these are going to be sharp corners or smooth or anything. I don't know anything about this graph. I've just sketched a picture of it. So this is kind of like a sketch of the derivative, right? It's going to go from positive to 0 to negative to 0 to positive because of the behavior of the function, the way the slopes of the tangents go from positive to less positive to 0 to flat to slightly negative to more negative to less negative to flat to slightly positive to a little more positive. Is what we're seeing. That's the story that this derivative is telling. Okay. Maybe I'll do another one. I'll do one with some kind of a discontinuity or something weird going on. Since, you know, this is already a really long video, I don't think there's really much harm in me recording, you know, some extra examples at the back end. If you've made it this far, you know, you must be pretty dedicated. So what I'm going to do is I might come through here and say, okay, I'm going to go over here. That could be just a good spot. Wait, hold on. This wasn't the best. It's supposed to have a slope of -2. And you can see it's not doing really the best ever, but it's fine. Okay. So it's like, you know, some kind of curved thing, and then we have a jump discontinuity in a line with negative slope. Okay, so if I want to sketch the graph of its derivative, oops, I'm losing the lead on my pencil. I'm going to need to say, okay, it goes from negative, and it gets flatter, so it's getting closer to 0. And then it does hit 0 at x equals 1. Did lose that lead. 0 at x equals 1. And then it gets a little more positive until at x equals 2, we have a jump discontinuity. So I know since it's discontinuous, the derivative will not exist at x equals 3. Okay? But after x equals 3, the slope of this line is always negative 2, meaning that after x equals 3, the derivative will always be negative 2. Okay, so after x equals 3, we'll have a constant negative 2. And I haven't really talked about, the derivative of a line or the derivative of a constant, the derivative of a curve. We haven't really talked about that yet. That's for a different discussion. Okay? But I'm saying that since the slope is constant here, this slope function is going to be constant in that sense. Okay, so it goes from negative to 0 to positive, and we'll say at its peak, maybe the max, it gets up to 1, or maybe 2, who knows. Some positive number up here. And it goes from negative to positive, and I don't really know how it's going, so I could just say, something like that. You don't really know. All right, not really sure where I was. Got interrupted and just got completely thrown off. I know that I see I've drawn the picture of f prime, so I think that, I think I explained this. I'm going to move on to do one more type of example, and then I'll wrap this video up. So this next one would be the kind of the opposite. And this would be, here's the graph of f prime. What does the graph of f look like? And there are definitely going to be limitations on what we can do here. Especially because we know so little right now, right? F prime is shown below. Sketch the graph of f. Okay. So I'm going to just do one, I'm going to do a couple and keep these pretty easy. Okay, so why don't we do something like that is going to be, and maybe that's x equals 2. And this is f prime. What is that going to look like in terms of the original? Now, the first thing I'll say is that we don't know where it's going to start off. We don't have enough information to say. We can only say that wherever it is, so I might not even, put in a y-axis here, because I don't really need to. I'll say that this is x equals 0. Okay, well, down here at x equals 0 and before, the slope of the line tangent is negative, right? So it's got to be, whatever it's doing, it's got to be kind of headed down that way. But it's getting closer to 0. And then at x equals 2, the slope is 0. So it goes from having a really negative slope to having a less negative slope to maybe having a 0 slope at x equals 2. Okay. Which just means that it's going to be flat right here. And then it goes to having a positive slope. But at first, it's a pretty small slope. So maybe it'll be kind of like just barely curving up. And then as time goes on, the slope gets a little more positive. So maybe it, it comes to like that. It's starting to curve up. Okay. So just to kind of, again, show you with some color, I'm going from over here. F prime is negative. Negative, negative, negative. Meaning that these slopes that correspond to these x values need to be negative. Okay, so this is pretty negative. It's one to the left of 0. Okay, a negative slope. Another negative slope at x equals 0. Okay, good. A less negative slope at x equals, like closer to 2, which is what I'm saying. It's getting flatter, but it is still a negative slope if we were to look closely. Then at x equals 2, we have a slope because f prime of 2 equals 0. Well, that means that the slope of the line tangent to the graph of f at x equals 2 is 0. And a 0 slope that's horizontal. Then, as we continue progressing, f prime goes positive, which means that I'm going to have positive slopes of tangent lines. So over here, okay, it's gone a little positive, a little to the right of 2, like here, it's positive, but not super steep. And then it gets a little bigger over here at a later x. So this is about as good of a picture as we're going to be able to draw of f for now. I think I'll do one with, some more interesting behavior than just a straight line. But what you'll see is that it actually is, we're going to kind of run the same analysis. We'll say maybe we go like that. Maybe it, decreases and then increases or something like that. Right? That would be something different. And then what I'll do is I'll just kind of draw an x-axis, no attempt at giving you any sort of y-scale, because we can't really tell. We don't know what it actually, the tangent slope just means it has to be headed that way. And we can kind of piece it together based on tangent slopes, but we don't know how much the function is actually increasing or decreasing relative to how big f prime is. That's kind of, again, one of the core concepts of the class. So, over here, we're going to start with, this is the graph of f prime. Always good to label. And it starts off with f prime is positive. Okay, and it's really positive at first. And then it becomes less positive. Okay, then we have a 0 slope. Okay, and then the slope is going to go negative. Okay, it's really negative for a while, and then it kind of comes back towards 0. And then after that, it's going to go positive again. Okay, so, but not very positive, right? It's just, so that means it's probably just going to have a pretty low trajectory as it's increasing. Okay, so at x equals 0, we know we are increasing a lot. So let's just say I started there, right? And we have a pretty steep slope of our tangent line from 0 to 2. So, it's really increasing. But as we get towards 2, we see that the slope is actually getting closer to 0. So maybe what I need to have happen is to have it kind of level off at 2, right? So what I should probably do is curve it, and then that would actually make sense with what the graph is telling me. Is that the slope starts off really steep, but then it gets shallower as it goes. And that's what I'd mark. Kind of this first tangent line right here, very steep. That second one at x equals 1, not as steep, right? It's half the slope. And then at x equals 2, it's pretty close, or getting close to x equals 2, it's pretty close to 0. Okay, then in blue is going to be where the graph has a negative slope. Okay, so, and then it gets more negative for a while, but then it actually comes to the point where eventually, and this is at x equals 5, so I need to space this out a little bit. At x equals 5, we've got another flat spot. So that's a way that you could start, and this is usually a multiple choice question, but you can start by kind of saying, where do the flat spots have to be? Well, if I know the derivative is 0, I know I have to have a horizontal tangent. So I'm going up here, and then it's just kind of increasing a little bit. And that's about all we can say for that. And I think that's where I'm going to stop. This video's been an hour. If you stuck with me, then this is all sorts of different examples. But this is, one of the main concepts in calculus.